Welcome to this session of our class. So, we are looking into the module design of a membrane module design of an actual case where osmotic pressure is quite significant, and we are looking into the spiral wound module, that is the flow through a channel. And as we have seen, we have derived the governing equation of governing equation of axial pressure drop, governing equation of velocity in the retented channel, and governing equation of concentration. We have seen that these are basically ordinary differential equation. For the axial pressure drop, it will be a second order ODE. For the velocity, it will be a first order ODE, and the concentration, it is a first order ODE. So, three ordinary differential equations have to be hooked up, but there are membrane surface concentration that will be coming all the time in the picture. So, this membrane surface concentration has to be related to the bulk concentration, and as you have seen that this is related through the definition of mass transfer coefficient, which will be resulting an algebraic equation. So, ultimately we will be landing up into the a set of ordinary differential equation coupled with algebraic equation. It is a DIE system, differential algebraic equation system. So, let us just continue with that and finish up this problem. So, we have already seen that mass transfer coefficient, the algebraic equation that will be connecting the membrane surface concentration and bulk concentration through this equation, but k is also a function of x. So, this is the relationship between k and x, and let us look into what is I. I is the definite integral 0 to infinity exponential minus eta cube by 3 minus 0.42 lambda eta d eta, and lambda is the length average permeate flux, dE, that is the equivalent diameter, L u d square is the u is the velocity, and d is the solute diffusivity to the power 1/3, and Vw bar is nothing but 1 over L 0 to L Vw dx. So, this is the length average permeate flux. So, this has become, so we will be having three ordinary differential equation and one algebraic equation has to be solved. So, this is very complicated situation now, because the integration I also involve the length average permeate flux. So, what is the algorithm? So, we will be having three. Let us just summarize what we are having. This cannot be solved analytically like the earlier cases. So, we will be having three ordinary differential equations, and these equations are basically governing equations for delta P, governing equation of U, and governing equation of C concentration, bulk retented concentration, and one algebraic equations. The algebraic equation is the relationship between Cm and C via definition of mass transfer coefficient k, which will be essentially a function of x, and that will be a function of I, and I will be basically function of Vw bar, or the length average permeate flux. So, what we will be doing? So, the algorithm goes like this. The algorithm will be like this. We assume Vw bar, a length average permeate flux. Once the length average permeate flux is assumed, then I can be estimated once I can be definite integral, I can be estimated by using a trapezoidal rule. Then I can get k as a function of x. Once I get the k as a function of x, then I can go to the relation between Cm and C, can estimate the value of Cm, and then we will be hooking up this equation with the DIE system. So, this 4 will be basically the algebraic equation, and 3 ODEs, let us say by RK4 algorithm. So, 3 ODEs and one algebraic equation, this will be formulating a DIE system, or differential algebraic equation system, and this has to be solved simultaneously, and then we will be in the process what will be getting the output will be we will be getting k as a function of we will be getting VW as a function of x, delta p as a function of x, c as a function of x, u as a function of x, and Cp as a function of x. After that, what we will be doing? We will be finding out the average length average permeate flux as 1 by L 0 to L Vw dx, and we will see whether this length average permeate flux is coming close to the gauge value or not. If this is not coming close, then we have to assume another value of length average permeate flux and redo this calculation. So, this will be very complicated, and it will be basically at every step of RK4 this algebraic equation has to be evaluated by using Newton-Raphson method. So, Runge-Kutta 4 nested in with Newton-Raphson method at every step of RK4, and then the whole loop will be there will be an outer loop which will be carrying at a particular value of x. So, this will be continued till it goes for the goes for the full length of the channel at a particular x. So, this whole calculation has to be calculated as the particular value of x, and then it has to be we have to go forward for a x plus delta x if it is converged, and likewise we have to do the calculations at every x location. We have to calculate the permeate flux, then you have to do a length average permeate flux using Newton-Raphson, then you have to check whether this calculated average permeate flux will be coming close to the guess value or not. If not, then we have to iterate. If yes, then we will be getting a converged solution. So, likewise in an actual module system, the whole calculation to be done and the module can be designed. So, at the end of the design, what you will be getting? You will be getting a length average permeate flux, length average permeate concentration, axial pressure drop across the module. So, once you know the actual pressure drop across the module, one can select a pump which will be suitable to pump the fluid to overcome this pressure drop across the module. So, that completes the module design in an actual scale, and similar thing can be translated to a tubular channel or tubular module as well. So, next we will be going to our next topic, that is the dialysis operation, and dialysis becomes very important in most of the membrane based separation process, but there is a basic difference of dialysis between the pressure driven processes, and this is the major driving force in dialysis is concentration gradient. Concentration gradient. So, we will be having a feed chamber. Okay. There will be two chambers, those will be separated by the membrane. We will be having a feed side or feed chamber, and then we will be having a dialysate side. Dialysate chamber. So, in a continuous system, feed is going into the feed side, feed in, and feed is going out, and from here it is a counter current. Let us say we have seen the counter current is always effective, dialysate in, and here we will be having the dialysate out. So, the solutes which will be having a very small size and molecular weight, they will be having zero concentration here, and they will be going from feed side to the dialysate side. We are maintaining a dialysate flow rate. So, therefore, whenever the targeted solutes of small molecular weight or size, they will be permeating through the membrane, coming to the dialysate side, immediately they will be washed away. So, the concentration maintained in the dialysate side will be almost equal to 0. So, therefore, we are maintaining the maximum concentration gradient of solute, targeted solute from the feed side to the dialysate side. So, therefore, one can expect a very high mass transfer across the membrane module. Now, let us see what are the different the transfer resistances, those are involved in the dialysis process. So, diffusion flux, diffusion is the main mechanism. Is the because of the concentration gradient. So, let us say Ni is the mass flux of ith species across the membrane. So, this will be nothing but dim dcim dx. Okay. So, so this is nothing but dim delta c im by L. Dim is the diffusivity of ith solute in membrane matrix, and delta Cim is nothing but the concentration difference in the feed site and the of ith species from the in the feed site and the dialysate side. So, these will be Ni will be nothing but dim over L Cim in the feed site minus Cim in the dialysate side. So, the determination of dim is very important. So, if we can determine the concentration, the diffusivity of solute in the membrane matrix, then by measuring the concentration in the feed site in the dialysate side, we can really look into the we can really find out what is the total the molar flux or the mass flux across the membrane. Now, let us look into the different type of resistances, those will be appearing in the dialysis process. So, there will be apparently 3 resistances one can come across during a dialysis process. So, one will be the feed site resistance, a mass transfer coefficient, mass transfer boundary layer in the feed site, and there will be a mass transfer boundary in the dialysate site, and there will be the membrane resistance. So, there are 3 resistances we will be encountering. One is Rf in the feed site, and there is Rd in the dialysate site, and this is the membrane. So, Rf is liquid film resistance in feed site, Rd is liquid film resistance in dialysate site, and di and this will be the diffusivity in the membrane. So, this is the membrane resistance. So, let us write down the mass flux of ith species. This will be nothing but Cif bar minus Cif divided by Rf. This is across film in feed site. This bar representing the concentration in the bulk. This will be equal to dim divided by L Cif minus Cid. Cif is the ith species concentration in the feed and in the dialysate site. Dim is the diffusivity of ith species in the membrane matrix, and L is the membrane thickness. And there will be dialysate site resistance Cid minus Cid bar divided by Rd. So, now we can add this all up and see what we get. So, we will be getting an overall resistance. So, from the 3 equations we will be getting Cif bar minus Cif is equal to Nirf, Cif minus CID is equal to Ni L over DIM, and then CID minus CID bar will be giving you Ni RD. If we add all them up, then these will be cancelling out, and you will be getting CIF bar minus CID bar is equal to Ni. All the resistances are added in series. So, we can get an overall resistance Ni is equal to CIF bar minus CID bar and divided by R overall. So, overall resistance can be written as Rf plus L over DIM plus Rd, and you can write the overall mass transfer coefficient. So, K overall is equal to 1 over K in the feed side plus L over DIM plus 1 over K in the dialysis side. These K's are basically the mass transfer coefficient. So, one can get an expression of overall mass transfer coefficient as 1 over Kf plus L over DIM plus 1 over Kd. So, this will be the expression of overall mass transfer coefficient. So, once we get the overall mass transfer coefficient, we will be able to get the net mass flux across the dialysis module from the feed side to the permeate side or the dialyzed side. So, net mass flux across the membrane from feed to dialyzed side. So, that will be giving you a system in for a counter current flow So, C in, C out in the feed, C in dialysate, C out in dialysate. Typically, in the dialysate we will be getting the pure solvent. So, typically C in the dialysate side will be 0, it will be some finite value in C out. So, this will be exactly like a counter current heat exchanger. The analogy is counter current heat exchanger, and in our heat transfer course we have already found out that how the overall heat transfer that is taking place in a counter current heat exchanger. Now, in the case of dialysis, it is instead of a counter current heat exchanger, it is a counter current mass exchanger, and we can write down instead of overall heat transfer coefficient, we can write the overall mass transfer coefficient. Delta T log mean temperature difference can be replaced by delta C LMTD. So, we can write down the mass flux, mass flow rate kg per unit time, kg per hour will be nothing but K0 A delta C LMTD. What is delta C LMTD? K0 A delta C out, delta C in minus delta C out divided by ln delta C out divided by delta C in divided by delta C out. Okay. So, this will be the expression of mass exchange or mass transfer across the channel, and K0 is the overall mass transfer coefficient. And we have already obtained, we have already seen the expression of overall mass transfer coefficient. It will be 1 over Kf plus L over DIM plus 1 over K in the dialysate side. So, therefore, we know the mass transfer coefficient in the feed side, we know the mass transfer coefficient in the dialysate side, and if we can determine what is the diffusivity of the solute we are talking about in the membrane phase, we can calculate the resistance offered by the membrane L by dm. L is the membrane thickness. This can be determined if we put a cross section under the scanning electron microscopy. We can estimate the thickness of the membrane, but DIM may not be possible to know directly. So, there are if somehow we can estimate the value of diffusivity of ith solute within the membrane matrix, we can evaluate the overall mass transfer coefficient. Once we can evaluate the overall mass transfer coefficient, we can find out the concentrations in all the streams coming out of the system going into the system. Once we get that, we will be able to estimate the delta CLMTD term, and once if we know the value of DIM, if you know the membrane area, we can find out what will be the mass that will be transferred through the dialysis per unit time. If the concentration is fixed, mass exchange is fixed, we can evaluate what is the area of the dialysis membrane that is required for designing such purposes. So, once we know you can determine DIM, this equation can be utilized for the design purposes. For a given design, this equation can be utilized for the simulation purposes as well. Now, in the next, what we are going to do? We are going to do how to evaluate the method or procedure, how to evaluate the diffusivity of ith species within the membrane matrix. For that, exactly like the case of permeability and radial retention, we would conduct an independent set of experiment in a small batch dialysis process or small batch dialysis cell. So, let us look into the batch dialysis analysis. In a batch dialysis analysis, there will be no continuous flow. The cell is exactly the same like before. The two chambers have to be separated by a semi permeable barrier, whereas the volume of the feed chamber is Vf, volume of the dialysis chamber is D. We put a dialysis solution in the dialysis chamber. In most of the cases, it is pure water, and we will put a solution in the feed chamber, and there will be mass exchange from the feed side to the dialysate side. Now, Vf and Vd are volumes of feed and dialysate chambers, and the solute will be permeating from the feed chamber to the dialysate side. Now, we should have stirring here as well as there. So, a very good stirring will be preventing formation of any film over the membrane surface. So, continuous and efficient stirring is required. That will lead to prevention of formation of any film resisting the solute movement, any film over membrane surface, okay, both in feed side and in dialysate side. So, if that is done, we do not have RF and we do not have RD in this case. So, there is a stirring should be provided. So, what resistance is existing? It is the membrane resistance DIM over L. So, membrane resistance should be there, resistance due to membrane only. So, next what we are going to do, we are writing the solute mass balance in feed chamber and in dialyzed chamber. If you do that, the accumulation should be the material that is going out of the system. So, accumulation will be d dt of CID times VD is equal to AM DIM divided by L CIF minus CID. So, this is the solute balance in the dialyzed site. So, this is the accumulation of solute in the dialyzed chamber, and that is the material. This accumulation is because of the material, that is the solute that is coming in from the feed site. Similarly, we will be writing the solute balance in the feed site. So, that will be equal to the amount of solute that will be going out of the feed site. So, it will be a depletion in the case of feed chamber. So, d dt should be equal to CIF VF is equal to minus AM DIM over L. The amount remains same, CIF minus CID. So, this is the feed site solute balance. So, dialyzed site will be enriched by the solute transport, and the feed site will be stripped by the solute transport. So, what will be the boundary initial conditions at for both of them? At t is equal to 0, we have CIF is equal to CIF naught, and t is equal to 0, CID equal to 0. So, it was a pure dialysate initially, there is no solute present there. So, CID was 0, and in the feed site there is a feed concentration corresponding to CIF naught. Now, these two equations have to be solved simultaneously, these two ordinary differential equations, initial value problem. So, they are, since their initial conditions are specified, these are basically the initial value problem. These two equations have to be solved simultaneously in order to get the concentration profile in the dialyzed site. So, we take a sample from the dialyzed site and monitor the concentration of the solute in the dialyzed site, and then we will be comparing with the theoretical value of the experimental profile of the concentration in the dialyzed site should be compared with the predicted or the theoretical values, and from that comparison the value of DIM will be evaluated. So, I will stop in this class. In the next class, we will show how the value of DIM will be coming out from this analysis. Thank you very much.